All right, so in this question, we prove a sort of variant of Fermat's little theorem. Recall that the original theorem states that if you're working mod p, then a to the p minus 1 is always congruent to 1. So in this question, we'll show that if you're working mod p squared, a to the p times p minus 1 is always congruent to 1. So it's sort of an extension of Fermat's little theorem. So for the first part of the proof, as sort of building it up, we'll say how many integers are there such that GCD of x and p squared is equal to 1. And so GCD of x p squared is equal to 1. Recall that this is true if and only if x p squared coprime. Share no factors. And so recall that the factors of p squared are just a set of 1, p, and p squared. 1 and p squared are because the number has to be a factor of itself, and 1 is a factor of everything, and p is also a factor of it. And because it's the power of a prime, there's no way to factorize p further, and so we know these are all of the factors. And so if x is not coprime to p squared, this implies that p divides x. So x is equal to either p or 2p, etc., etc. Minus 1 times p. Recall that because x is less than or equal to p squared minus 1, then x is equal to p times p is equal to p squared, not allowed. Yeah. So we can have x having all of these values, blah, blah, p, 2p, etc., and p minus 1p. But we could also have x is equal to 0, which I forgot earlier. So in total, it's easy to see there are p possible values for x. So p is not coprime. So there are p squared minus p ints that are coprime, because recall that we're working in the range, we're working mod p squared, so there are precisely p squared total numbers in our space. And you'll notice that this p squared minus p can be factorized into p times p minus 1, which should be suggestive because that is exactly the number we have up here. So you can think about, well, spoilers for the next question, but you'll think about reasoning about the numbers of this set and the size of this set and the like.